So the idea behind the encoder is increase the minimum distance at the cost of spectral efficiency. The idea behind the decoder was the following. You have a received signal Y, and the job of the decoder is to find x hat, which belongs to the signal set, so that you minimize your probability of error. And the probability of error is x is not equal to x hat. That's the probability of error for your decoder. And we saw a bunch of equivalence rules. We said that the minimum probability of error rule, which is this rule here, is same as the maximum a posteriori rule, and this just follows by the definition. This was same as the maximum likelihood rule, and here we made one assumption that all the signals in your signal set A are equally likely, and this was shown to be equivalent to your minimum distance decision rule. And in order to show this equivalence, we used the fact that the noise was white and Gaussian. So this assumes equiprobable signals. And this assumes AWGN channel. Okay. In fact, the minimum distance decision rule has very nice geometrical properties. We basically said that the decision regions had a particular shape. They were convex polytopes, and they were also known as Voronoi regions. However, finding the exact expression for the probability of error seemed quite tedious. So we decided to settle with bounds, and we developed some bounds for the probability of error. And the main bounds were, we had a strict upper bound, which was this summation. Okay, this is a strict upper bound. Well, the inequality here says it's a strict upper bound. We also had a union bound estimate, which said, because this is a sum of various Q functions, this is still a very cumbersome expression to evaluate. So we wanted a simpler expression. So we then approximated this by K min of AJ times Q of D min over 2 sigma. Okay. And now if we take the average on both sides, what we get is that probability of error is approximately equal to K min of the constellation, which is the average number of nearest neighbors, times Q of D min over 2 sigma. Okay. And this expression is known as the union bound estimate. We call it an estimate because it's not a bound anymore. We have made an approximation in going from here to here. So this is what we came up with last time. Throughout the analysis today, we will be, whenever we have the probability of error expression, we will be estimating it by the union bound estimate. So this union bound estimate is quite important. Are there any questions on this? Okay. So today we will start by introducing the notion of effective coding gain. And we will use the symbol gamma sub f for that. what do we mean by effective coding gain? First, we have to decide what regime we are operating in, right? It's defined for both bandwidth limited regime and power limited regimes. So let us start with the power limited regime. Remember, in the power limited regime, the trade-off we care about is the probability of bit error versus EBNO. The baseline scheme is 2 PAM. And for 2 PAM, we showed, like 2 lectures ago, that the probability of bit error is given by Q of root 2V over N naught. Okay, this should be. So now the idea is to plot your probability of bit error as a function of EBNO. EBNO is always plotted in dB on the x-axis. The probability of bit error we also plot on a logarithmic scale. So this is 10 to the minus 6, this is 10 to the minus 5, 10 to the minus 4, and so on. The Shannon limit is at, this is the Shannon limit. It's at minus 1.59 dB. Okay, for the power limited regime. The performance of 2 PAM, which is given by this expression, is here. And we basically said that when the probability of bit error is 10 to the minus 5, the gain that the EBNO that you require is 9.6 dB. This is a 9. Okay. So what's the idea behind the effective coding gain? Well, suppose I give you a certain constellation, okay, a certain signal set, and you find the probability of bit error for that, and you plot it, and it comes out to be something like this. So this is the performance for some given signal set A. This is your 2 PAM. Okay. And now you want to quantify how much better is this signal set over the baseline system. Now, so in other words, you want to look at the gap between the two curves. Now, clearly the gap is going to be a function of your probability of bit error, right? But the basic idea now is you want to fix a certain probability of bit error, because if you're designing a system, the probability of bit error is something that your system tolerates, and it's going to be fixed throughout the analysis. So in this course, we'll be fixing it at 10 to the minus 5. You fix this probability of bit error to 10 to the minus 5, and you look how much gap you have between the two curves. And this gap is going to be your effective coding gain in dB. Okay. So in other words, effective coding gain, I can write here, is the gap between a given signal set and the uncoded system 2 PAM at a fixed probability of bit error. Okay, so now let us try to quantify this effective coding gain using the union bound estimate that we have here. So if I have a certain signal set A, then I know from the union bound estimate that the probability of error is given by K min of A times, well, approximately Q of D min over 2 sigma. So since I want an expression in terms of probability of bit error, I will use the fact that probability of bit error is probability of error per symbols over the number of bits per symbol. Since I have m points in my signal set, I have log m bits per symbol. And this is then K min of A over log m base 2 times Q of d min over 2 sigma. Okay. So I'm going to rewrite my probability of bit error expression now in this, in fact, the right hand side in this form: KB of A times Q of root 2 gamma C of A times EB over N naught. So I'm just going to define the right hand side in this way. And I'm going to relate gamma C of A and KB of A to the parameters I have on the right hand side there. Okay, and why do I want to do it this way? Because I want to get an expression as close as possible to the performance of an uncoded 2PAM system, because that way it will, things will be easier to, if I want to calculate the effective coding gain. Okay, so how do the parameters relate? Well, KB of A is K min of A over log m to the base 2, and this is the average number of nearest neighbors per information bit. Okay. If I compare the arguments inside the Q function, what I have is 2 gamma C of A times abno is the argument d min over 2 sigma square, which I will write it as d min square over 4 sigma square. So now if I were, remember sigma square is n naught over 2. So if I simplify this expression, what I will end up getting is gamma C of A is d min square over 4 EB. Okay. Gamma C of A is known as the nominal coding gain. It's not the same as the effective coding gain, which is the distance between the two curves. Okay? Are there any questions so far? So far what I have done is, given a constellation A, I can find two parameters. Okay? I can find the nominal coding gain, and I can find the average number of nearest neighbors per information bit. And using these two parameters, we will try to get a handle over the effective coding gain. So that's the idea. So how can we plot? So given this constellation A, we want to plot the probability of bit error curve like this. But instead of plotting the exact curve, we will be plotting this curve here, which is the union bound estimate of your probability of bit error. So we'll be always plotting the union bound estimate. So how do we do that? So we'll again start with a curve like that. Probability of bit error as a function of abno. This is in dB. The y-axis is also in dB. Sorry, not in dB, but on the log scale. And so on. This is the Shannon limit at minus 1.59 dB. This is the 2PAM performance curve. So if we want to plot this union bound estimate, we will be doing two steps. First, we'll be plotting this Q function, a curve corresponding to the Q function, and then we'll be scaling it. So how will the Q function, if I just want to plot this Q function, how will it compare to this curve here? Well, you're just scaling the argument inside the Q function, right? But now, because we are plotting the x-axis on a dB scale, it simply means that we are translating to the left by an amount of gamma c in dB. Is that clear? Well, see, what we are doing is we are going to scale the x-axis by a certain constant. So this means that we will have to scale the x-axis here. But our EBNO is being plotted on a dB scale, right? So multiplying in the linear scale corresponds to an addition on the logarithmic scale. And an addition on the logarithmic scale simply implies a shift on the x-axis. So that's the constant shift on the x-axis. So I'm going to plot it here. This curve is going to be parallel to the original 2pm curve to the best of my abilities. Okay? So this is what we get as your Q function. Now we are going to scale the y-axis by this factor here, kb of a. But remember, the y-axis is also on a logarithmic scale rather than a linear scale. So multiplicative factor of kb of a implies a vertical shift by a certain factor. So I'm going to do a vertical shift here. Now I'm going to plot. So let me make that curve darker now. So this is what I end up getting. Okay, now note that the distance between these two curves is not fixed anymore. If the slope is steeper, then this distance is small, meaning that this distance here is large. On the other hand, if the slope is going to be smaller here, then this distance is large. Okay? So this means that the distance between these two curves is no longer fixed. And basically what we are saying here is that if the probability of error is large, then the number of nearest neighbors matters much more. But if the probability of error is going to be quite small, then the more important factor is your exponent, how fast the slope decays, as opposed to the number of nearest neighbors. Okay? This distance here is your effective coding gain. And this constant horizontal distance here is your nominal coding gain in dB. Are there any questions on this curve? Yes.
The new curve, is it on the right of the whole 2pm, because these are, we add the logarithm. I mean,
so what I'm really assuming is gamma c of a is greater than 1. Right. So if I'm adding it, then I'm going to shift to the left, right? Okay, so a couple of remarks. I'm just summarizing a few remarks I made while plotting the curve. First is the log-log scale is very convenient. Because any multiplicative factor simply involves a translation along the x and y directions. The second point is that the accuracy we have in the effective coding gain in this way is within, is determined by the union bound estimate, because that's all we are plotting. We are not really plotting the exact curve. Okay. And the third point is that we have a rule of thumb. Now, because the distance between the two curves is not fixed, it seems still tedious to find the exact numerical value of effective coding gain. So but we can find the value of the nominal coding gain and kb of a exactly given a constellation. So we want to have a rule of thumb for the effective coding gain. And the rule of thumb is that the effective coding gain is given by the nominal coding gain in dB minus 0.2 log 2 of kb of A. This is in dB. What this means is every factor of 2 increase in kb results in a loss of 0.2 dB in the effective coding gain. Okay, so this is at probability of bit error of 10 to the minus 5. So that's the regime that we will be doing our analysis in. So this rule of thumb is quite helpful. Are there any questions? This rule of thumb? Well, it works quite well in practice. So you want to use that rule of thumb.
And here the y-axis also in log.
Right.
Decimal.
Okay. So if things are clear, let us do some examples. So let us start with a 2 PM. So examples. The first is 2 PAM system. What's the effective coding gain going to be for this constellation? It's going to be 0 dB, right? It just follows from the definition. I mean, what effective coding gain tells us how much gap we have between this new constellation and 2 PAM. If your new constellation is 2 PAM itself, we don't have any effective coding gain. What about a 4 QAM? It's going to be still 0 because a 4 QAM is a Cartesian product of two 2 PAM constellations. And we argued last time that there is no coding gain if you use a Cartesian product. If you want to verify it using the framework that we have just developed, say we have 4 points. This point is alpha, alpha. This point is minus alpha, alpha, minus alpha, minus alpha, and alpha minus alpha. The nominal coding gain is given by d min square over 4EB. The minimum distance is 2 alpha between any 2 points. So we have 4 alpha square. What's the energy per bit? Well, energy per symbol is 2 alpha square. Then we have 2 bits per symbol, so the energy per bit is alpha square. So we have 4 alpha square, and so that's 1. So we do not have any nominal coding gain. KB of A, what's that going to be? Well, we have 2 nearest neighbors per symbol, but we also have 2 bits per symbol. So the number of nearest neighbors per bit is going to be 1. So your nominal coding gain is 1, and KB of A is going to be 1. And so we do not see any any coding gain for the 4 QAM system. Now let me do a slightly different case. Let me start with a 4 QAM, but I remove 2 points. I remove this point, and I remove this point, and I only keep the 2 points here. So I have a constellation, say, A prime, which only has 2 points, 1 point here and 1 point here. So this point is alpha, alpha, and this point is minus alpha, minus alpha. Any idea what the effective coding gain will be for this case?
I think it's saying.
It's still 0, right?
Yeah, because it's 2 is saying as 2 PAM.
Exactly. All this is a 2 PAM constellation embedded in 2 dimensions. It's 2 PAM along this line, right? So I cannot hope to have a higher coding gain for this constellation over the original one. I mean, I told you the story that we can take a subset of points and we can increase the minimum distance by throwing away some points. But one has to be careful in that analysis. There could be examples where you're strictly improving the minimum distance. Note that the minimum distance here is going to be 8 alpha square now. Okay, so the minimum distance is strictly improved. But what happens to your energy per bit? Well, the energy per symbol is 2 alpha square, but we only have 1 bit per symbol. So the energy per bit is 2 alpha square. So your nominal coding gain is d min square over 4 EB, which follows from the relation we have here. And d min square is 8 alpha square, 4 EB is also 8 alpha square, so the nominal coding gain is 1 or 0 dB. The average number of nearest neighbors, well, we only have one nearest neighbor, and we have 1 bit per symbol, so that's, and this is A prime, by the way. It's going to be 1, and so the effective coding gain is still 0 dB. So probability of symbol error as a function of alpha has definitely decreased, right? But the trade-off we care about is probability of bit error as a function of EBNO. In other words, this curve is still here. It's not changed. I just shifted right by reducing my spectral efficiency. Okay? So let's do one last example just to prove that it's not always the case that you get nothing by removing points. Okay. So the constellation that I have in mind is this, the one I introduced last time. We start with a threefold Cartesian product of 2 PAM. Okay, so in 3 dimensions it's a cube, and the threefold Cartesian product will have a point on each of the vertex of the cube, and we only keep 4 points. So the points we keep are these 4 points. Okay, so I write B, the coordinates are alpha, 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 minus alpha, minus alpha, alpha, minus alpha, alpha, minus alpha, and alpha, minus alpha, minus alpha. So these are the these are the coordinates of the 4 points here, where we have the standard x, y, and z axis, which I'm not drawing because it will just look confusing. So now we'll see that for this particular signal set, we do have a coding gain. Okay, let's find the minimum distance. The minimum distance here is what? It's the distance along a diagonal, and the diagonal is of length 2. Each side of the cube is of length 2 alpha. So the diagonal is of length 2 root 2 alpha. So d min square is 8 alpha square. Okay. What is the energy per bit going to be in this case? And what's the energy per symbol now? 3 alpha square over 2 is the EB, right? We have 3 alpha square units of energy per symbol. We have 4 points, so we have 2 bits per symbol. So the energy per bit is 3 alpha square over 2. So now if I look at my nominal coding gain, that's going to be d min square over 4 EB, d main square is 8 alpha square, 4 EB is 6 alpha square, so that's 4 over 3. On a linear scale and on a dB scale, this is going to be you guys should remember your dB tables.
0.12.
1.2. You have to multiply by 10. So it's right. So actually, I think it's 1.3, more like 1.3 dB if you look at the last significant digit. Okay. So what's KB of A going to be in this case? Or KB of B, I should say. This is, I'm calling the signal set B here. So what is KB of B going to be? 3 by 2, right? You have 3 nearest neighbors per point. For each point has 3 nearest neighbors. They are all equidistant. And you have 2 bits per symbol. Okay? So if you work out your effective coding gain using this rule of thumb here, you take gamma C of A in dB and subtract 0.2 log 2, you will see that the effective coding gain is approximately 1 dB. Are there any questions? Okay, so it might seem that this is still not a very impressive number. Yes, you had a question.
Just what was it about this constellation that gave us coding gain? It's the fact that we went to higher dimensions and
right. It's more, so basically, usually you do get a coding gain if you trade off minimum distance with spectral efficiency. So that's usually the case. So that's one representative example of that case. This was a very special case where you ended up with a 2 PAM constellation to start with. Okay. So the comment I was going to make is that 1.0 dB still might not be like a very impressive number. I mean, after all the hard work, you just get 1 dB effective coding gain. So question to ask at this point is, are there any constellations that have much higher coding gains? In particular, are there constellations that come close to the Shannon limit at all? Okay, and we look at one interesting class of signal sets, which are known as orthogonal signal sets. And you probably saw these examples back in 450, but we'll just reviewing it again here. And these signal sets have a property that as you increase the number of dimensions, you come arbitrarily close to the Shannon limit. So the definition of these signal sets is your A, it's a collection of signals AJ, where J goes from 1 to M, such that the inner product between AI and AJ is EA times delta IJ, meaning that if I is not equal to J, the two signals are orthogonal, and if I equals J, the energy is EA. Geometrically, when we have 2 points, the 2 points can be thought of as 2 points on the 2 axes. So this is the case when M equals 2. When M equals 3, the 3 points will lie on those 3 corresponding axes. So this is the case when M equals 3 and so on. So generally, when you have M points, your signal space lies in M dimensions, and each point can be thought of as a point on one of the axes. So the minimum, so if you look at the distance between any 2 points, it's the norm of AI minus AJ square. I could simplify this simply as the norm of AI square plus the norm of AJ square, because, well, the inner product is going to be 0. Okay. Now AI square is going to be EA, AJ square is going to be EA, so this is 2EA. So what we are saying here is that every point is equidistant from every other point, and the distance, square of the distance is 2EA. Okay. So in other words, the average number of nearest neighbors is always going to be m minus 1. Okay. So let us calculate the nominal coding gain for this constellation. That's going to be d min square over 4EB. D min square is 2EA over 4EB. Well, the energy per bit is the energy per symbol, which is EA, over the number of bits per symbol, which is log m to the base 2. And this I'm going to write here is log m to the base, half log m to the base 2. So as I increase my m, my number of dimensions, my nominal coding gain goes to infinity. Okay. What do you expect for the effective coding gain? Will it also go to infinity, or? Well, we don't know whether it approaches Shannon limit as of yet, but we know it cannot go to infinity. It's upper bounded by the Shannon limit, right? So the effective coding gain cannot really become unbounded. And what's happening really here? Right, but why does the effective coding gain stay bounded and the nominal coding gain blow up? Right. The number of nearest neighbors also increases with m, right? Not just the nominal coding gain. Okay. So let's write that down. If I look at the number of nearest neighbors per information bit, yes?
These don't have zero mean, right?
Right, they don't have zero mean. That's a good point.
Close the Shannon limit, probably we have to make the mean to zero, no?
Let's see. What happens to the mean as m goes to infinity? If you look at what happens to the mean, it will be 1 over m. If you find the mean of this guy, it's half times the distance here times distance here. It's half EA, comma EA. Okay? If you look at 3 dimensions, it's 1/3 EA, comma EA, comma EA. So in m dimensions, it's going to be 1 over m times all these coordinates. If you look at the mean square, it goes to 0 as m goes to infinity. So that's a good point. So it does, the mean does go to 0, and so we approach the Shannon limit. So we have kb of a over log m. What's the number of nearest neighbors? We saw it was m minus 1 over m over log m, and that goes to infinity as m goes to infinity. Okay, so the nearest neighbors, the average number of nearest neighbors per information bit also go to infinity. as m goes to infinity. And if you look at the mean, just to write down the comment that was made, if you look at the mean of this constellation, that's going to be 1 over the number of points times root EA, and root EA. So we have, these are m coordinates. So that's going to be the mean if you believe this is the coordinate axis here. And if you look at the norm of MA square, then it's going to be EA over m. And as m goes to infinity, this goes to 0. Okay. And because the mean goes to 0, it's not unreasonable to expect that the performance does approach to the ultimate Shannon limit. Okay. So far we have looked at KB of A and gamma C of A. If you look at the effective coding gain, it is still bounded. It's always bounded, but it is not clear at this point what really happens to it. And in fact, it's not quite straightforward to actually show what happens to the effective coding gain. If we have taken 6450, then Professor Bob Gallagher really goes into the details of proving how that the effective coding gain for this signal set indeed does approach the Shannon limit. Okay, but it can be shown that the effective coding gain does approach 11.2 dB as m goes to infinity. The main trick here is that union bound is usually quite weak if the probability of error is small. So we replace the probability of error just by 1 instead of the union bound at some point. And if you do that change, then things work out nicely. But in this course, we will just assert that the orthogonal signal sets to achieve the ultimate Shannon limit. And you can see 6450 notes for the proof. Okay. So that's the assertion that we are making right now. So let's take a step back and take a look at what's happening so far. We have a class of signal sets which are conceptually quite easy to describe. They're just orthogonal signal sets. They are not too hard to analyze, and they asymptotically approach the ultimate Shannon limit. So this seems quite nice, so why not we just implement them? Okay. Now, it turns out that these are not very common in practice. They are not implemented as often as you might think when you first look at them. And because they have some kind of drawbacks. And there are a couple of drawbacks which make them very less appealing than what you might otherwise think. And first of all, what's the spectral efficiency for these signal sets? It goes to 0. And how does it go to 0? It's 2 log m to the base 2 over m. As m goes to infinity, this goes to 0. And in fact, it goes to 0 quite sharply. Now, that's fine. Well, if you want to approach Shannon limit, our spectral efficiency should indeed go to 0. But if you're looking at the system design problem, what do you really want? You have a certain effective coding gain that you have in mind. And suppose you are presented with a list of several different signal sets that achieve this effective coding gain. And your job is to pick one of these possible signal sets. Which one will you pick? Well, there are two things you will look for, right? You will look for the spectral efficiency that these different signal sets require or achieve in order to get this effective coding gain. And the higher the spectral efficiency, the better. And secondly, you will also want to look at the implementation complexity. You do not want something which is really takes a lot of time to decode. Okay? So it turns out because the spectral efficiency goes to 0 so sharply, it's not very surprising that there are other codes that have the same effective coding gain but higher spectral efficiency. So there are binary codes that have a higher spectral efficiency for same effective coding gain. And so they would be a natural choice over the orthogonal signal set. Yes.
So you want a high spectral efficiency to use as little bandwidth.
Right, because in practice, bandwidth is never really infinite, right? So if you are achieving the same, the first objective is to have a certain effective coding gain. If you do have that, you want to pick something which has a higher spectral efficiency. And indeed, the subject of chapter 6 and 8 is to come up with binary codes that have much better performance than the orthogonal signal set for a given effective coding gain. Chapter 6 deals with the block codes, whereas chapter 8 deals with convolutional codes. And chapter 7 basically develops all the finite field theory that you require to study convolutional codes. Okay, so the point is, in the subsequent lectures, we will be focusing a lot on improving the performance over orthogonal signal sets. The second point I mentioned was implementation complexity. Now, one particular way of implementing orthogonal codes, which you saw in the first homework, was using this idea of Hadamard transforms, right? You have a Hadamard matrix, which is an m by m matrix. The rows of the Hadamard matrix are your orthogonal signal sets, which are elements aj. And at the receiver, what you would do is, when you get this received signal y, you simply multiply it by the Hadamard matrix and look at the coordinate which is the largest. So this is something you did in the first homework exercise. And how many computations did you require for an orthogonal signal set of size m? Sorry? Okay, so I meant m being the size of the orthogonal signal set.
Yeah. M dimensional.
Right.
It's a 2 to the m by 2 to the m.
If it is a 2 to the m by 2 to the m, it is m times 2 to the m. But if there are m orthogonal signal sets, then it will be m log m. Where m is the number of signal sets, right? So that's the number of computations that were required. Now, the question to ask is this fast or is this slow? Is this too many computations or is this too little computations? And if we are looking in the power limited regime, what we really want is to see the complexity per information bit, because we normalize things by per information bit. Now, how many bits are sent when you have an orthogonal signal set of size m? We have log m bits, right? So this quantity is actually exponential in the number of transmitted bits that we are sending. And so, in fact, this is quite slow. Or in other words of saying it is, we require m times 2 to the m computations, where m is the number of information bits that we are sending. So
if m is your size of your orthogonal signal set, then you have log m bits, right?
Right.
So m log m over log m is m.
Why are you dividing by m?
You need m log m operations to decode a symbol.
To decode a symbol.
And each symbol gives you log m bit. So you
Well,
you need m operations per bit. Right?
Well, when you have, say, log m bits, right, you can only send one of the m possible symbols. And when you want to decode this symbol, you end up recovering log m bits. So you should not be dividing by m here.
No, dividing by log m. Because you want to do it per bit.
Oh, right. You're right. So you're dividing by log. You have m log m bits. You're dividing by log m. So you have still m.
You have m calculations per bit.
You have m calculations
Per bit.
Per bit.
And that goes to infinity as m goes to.
Yeah, it's exponential in the number of iterations.
So we are sending. So I need this many computations to get log m bits. All right. So is this expression exponential in log m or not? So that's all I was saying.
Okay. Yeah, I just put it in the other way, that if you divide by log m, then it's
You have m information, right? Okay, are there any questions? I mean, we are both agreeing to the fact that this is too many computations than you would want. And there exists other decoding algorithms for which the number of computations is much smaller than exponential. Okay? Okay. So let's next look at the bandwidth limited regime. well, actually before that I wanted to mention a couple of other signal sets as well. So there's two other important class of signal sets which are related to the orthogonal signal sets. The first is this class of simplex signal sets, and the other class is bi-orthogonal signal sets. So the idea behind simplex signal sets goes back to the observation that was made that we have a non-zero mean for these signal sets here. So if we do, we can indeed subtract off the mean and get a performance which is better than the orthogonal signal set. So in particular, if I subtract off the mean here, I get a signal set which is like this. This is the simplex signal set when m equals 2. When m equals 3, I'm going to subtract off the mean from this plane here. The points lie on this particular plane. And what I end up with is an equilateral triangle. So this is the case when m equals 3. What do you think m equals 4 would look like? It's a tetrahedron. It's right here. Right? That's a simplex signal set. So basically, it's also not too hard to write an algebraic expression for the signal sets. E of a prime is going to be E of a minus m of a. Okay, you subtract off the mean from your signal orthogonal signal set. If I want to write in terms of inner products, the inner product between ai and aj is given by Ea if I equals j, and it's, I believe, 1 over m minus 1, minus of 1 over m minus 1 times Ea if I is not equal to j. So this is the inner product between ai and aj. And I mean, there are too many properties of these simplex signal sets, but I believe that that's going to be in your next homework exercise. So I'm not going into too many details. What's the spectral efficiency in this case going to be?
Yes. Sorry, I have a question. So, what is a simplex? A simplex just refers to anything with zero mean?
Simplex signal set is derived from the orthogonal signal set by subtracting off its mean.
Right, but in general, simplex means anything with zero mean.
I'm not sure of that. So what's the spectral efficiency going to be? Well, almost.
Divide, reduce one dimension.
Right, you just reduce one dimension. Okay? And there are other properties that you will be looking at in the homework. Now, the idea behind this.
1 over r is
This is 2 log m over n. Okay. So the idea behind the bi-orthogonal signal set is you start with an orthogonal signal set, and for each point you also put the negative signal of it. So instead of, in addition to this, you will have a point here and you will have a point here. So the case in 2 dimensions, n equals 2, you will have 4 points like this. So in this case, you are increasing the number of signal points by a factor of 2. But this does come at a price, right? Because if you're increasing the number of signal points, the number of nearest neighbors is also going to increase by a factor of 2. In this case, you have 2 nearest neighbors now. So you have both the effects going on. I mean, ultimately, all these signal sets as m goes to infinity are going to approach the Shannon limit. So again, but they do suffer from the same kind of drawbacks that we saw for the orthogonal signal sets. So these are more of theoretical interests as opposed to real practical implementation point. Any questions?
So the minus E over n minus 1, how would you get that?
It's a bit involved to show. I think you'll be showing it in the homework exercise. Or it was an exam problem at one point. So you basically start with the orthogonal signal sets here. Look at the inner product here. And use the relation between the simplex signal sets and the orthogonal signal sets. You're subtracting of the mean. And then you can derive the inner product expression. Okay, so let's now move on to the bandwidth limited regime. Okay, so the main difference between, yes?
Number by 2 or 2k signal points.
You mean here? For each,
For n, not n.
by a factor of 2. I said a factor, right? So if you have m points in the orthogonal signal set, you have 2 m points in the bi-orthogonal signal set. Because for each...
If you think of 3 dimensions, in orthogonal sets we have 3.
And in this you have 6. Okay. So let's look at the bandwidth limited regime. The trade-off we care about is the probability of error per 2 dimensions as a function of SNR norm. Okay. The baseline scheme here is your MPAM scheme. And we showed a couple of lectures ago that the probability of error per 2 dimensions is approximately 4q times root 3 SNR norm. Okay. So let's plot the performance graph. So on the x-axis I plot SNR norm. On the y-axis, I plot PS of E, again on a log-log scale. It's 10 to the negative 6, 10 to the negative 5, 10 to the negative 4, 10 to the negative 3, and so on. The intercept is at 0 dB, this point here. So this is your Shannon limit in the bandwidth limited regime. Now your performance curve is going to be something like this for the MPAM system. And we want to basically quantify now the effective coding gain in this regime. So it's the same story as in the power limited regime. We will start off with the probability of error using the union bound estimate, which is k min of A times Q of d min over 2 sigma. Now PS of E, it's the probability of error per 2 dimensions. Assuming we have n dimensions here, it's 2 times the probability of error over n. Okay, so this is probability of error per symbol. We are dividing by the number of dimensions and multiplying by 2 because it is per 2 dimensions. And this is going to be 2 times k min of A over n times q of d min over 2 sigma. So now let's do the same trick that we did in the power limited regime. We will write Ps of E be approximately, and instead of the right hand side I will write it as Ks of A times Q of root 3 SNR norm. Okay, but because I have a factor of 4 up there, I will also multiply and divide by 4. Okay, that's not going to change anything.
So PS of E is probably better for 2 dimensions or
Right.
per symbol?
Per 2 dimensions. In bandwidth limited regime, we normalize everything by 2 dimensions.
But for NPAN, we used it per symbol, right? The calculation represents.
No, it was
symbol.
per 2 dimensions. It was per- Okay, so now let's compare the two expressions. We have Ks of A, which we define by 2 times K min of A over n, and this is the number of nearest neighbors per 2 dimensions. And I can write 3 times SNR norm is d min square over 4 sigma square. Okay. Actually, I was missing this factor of gamma. I knew I was missing something. It's not just 3 SNR norm. It's 3 times this nominal coding gain times SNR norm. So 3 times SNR norms times gamma C of A here. So this is d min square over 2n naught. So what do I have for gamma C of A? It's d min square over 6 n naught times SNR norm. Remember, SNR norm is SNR over 2 to the rho minus 1. It's normalized signal to noise ratio. So this is d min square times 2 to the rho minus 1 over 6 times n naught times SNR. Well, n naught times SNR is just ES. So this is 6 times ES. So this is the expression you have for the nominal coding gain. Okay? So now again, given a signal set A, I can find those 2 parameters, the nominal coding gain and the number of nearest neighbors per 2 dimensions, and I can use those to plot on the PS of E versus SNR norm curve. So again, the exact same story. If I have a certain nominal coding gain, I will simply shift my curve along the x-axis by that factor as a pure translation. And then, because I have a factor of Ks A over 4, I'm going to plot, how did that expression go? This expression on the top. Remember, this curve here is 4 times root 3 SNR norm, right? So the multiplicative factor I have is Ks A over 4. So I will shift my curve up by that factor. And I will get something which is like this. And that's my union bound estimate for this new constellation A. The distance here is gamma effective this distance here is gamma c of A. Okay. Are there any questions? So now we also have a similar rule of thumb as in the power limited regime. I will write that rule of thumb here. We have that gamma effective is going to be gamma c in dB minus 0.2 times log 2 times Ks of A over 4 in dB. Okay, so again a factor of 2 in Ks will decrease your nominal coding gain by a factor of 0.2 in dB. Are there any questions? Well, so I mean this is the end of chapter 5. Still have like 10 minutes remaining, so I thought I will give you a preview of the next chapter. Professor Forney will come next class and he will be starting chapter 6 all over, I believe. This chalk is much nicer to erase than the other one. So in chapter 6, we will be looking at the binary block codes. Okay, and what's the main architecture of these codes? Well, for an encoder, remember we have k bits coming in, and we pass it now through a binary block code. And what we get out is a sequence of a binary sequence of length n. Okay, so x belongs to C, where C is a subset of binary sequences of length n. So we start with k bits and we convert them to n bits, where n is going to be greater than or equal to k. Once we have this sequence of n bits, what we end up doing is we pass it through a binary signal constellation. So I'm writing it as binary signaling, and what we get out is S of x, which is a sequence of n symbols, which each symbol can either take value minus alpha or alpha. So this binary signaling is actually quite a trivial step. Basically, the relation is S of 0 is going to be alpha, and S of 1 is going to be minus alpha. If I have a 0 coming in, I will produce an alpha. If I have a 1 coming in, I will produce a minus alpha. So this part here is trivial. All our energy will be focused on will be to find a good code. Given a sequence of input bits, we want to find a good binary code in order to maximize the minimum, in order to optimize the minimum distance and so on. So that's the architecture that we will be using for the binary linear codes. Both chapter 6 and 8 will be only focusing on this part, and this binary signaling scheme for most part will be implicit in our architecture. So at this point, one might ask, is there anything to lose in this, imposing this type of architecture? Remember, the nice thing about this architecture is we have coding which is going on here, and we have modulation that is happening here. And the modulation step is quite simple. So we have a separation between coding and modulation. Okay, and the question is this the right thing to do? Now it turns out that if we are going to live in this binary world, where we only constrain ourselves to send binary signals over the channel, this is in fact a canonical structure. There isn't much improvement we can get, and that is quite obvious, right? But it turns out that if we are going to go for non-binary signaling, particularly in the bandwidth limited regime, there is a cost to be paid for this kind of separation. In fact, in the 1980s, there was this whole idea of turbo-coded modulation or trellis-coded modulation, and the idea there was to combine coding and modulation in one step. So this is not optimal for non-binary signaling, but it's fine for, it's okay for binary signal. Okay, so we will be focusing on this type of an architecture. The other issue is, okay, nobody told us that you can only send binary signals over the channel. If you want to achieve the Shannon limit, when we derive the capacity expression, or we just stated it, but you can derive it, we said that the Shannon limit is rho is less than log 2 1 plus SNR, and we never said that we can only send binary signals over the channel. So it could be that there is some inherent suboptimality in this type of an architecture. Why send binary signals in the first place? Again, it turns out that the regime that we are interested here is the power limited regime, because the spectral efficiency can never be more than 2 bits per 2 dimensions, right? Remember, rho is 2k over n here, and k is going to be less than n. So we are inherently in the power limited regime, and so a natural thing to do in order to understand how much fundamental loss we have in imposing this type of binary constraint over the signals is to not look at this expression, but to find the best possible performance we can have if we constrain ourselves to binary signals over the channel. If we impose a certain signaling constraint, we can find another fundamental limit on the spectral efficiency. So the point being, the best possible binary code can only achieve this upper bound here. Now this upper bound has to be less than log 2 1 plus SNR, right? Because the Shannon code assumes the binary signaling as a special case. So it turns out that this expression is actually quite tedious to write out. I'm not even sure if the closed form expression exists, but you can calculate this numerically. It's just some kind of a convex optimization problem. And now, in order to understand how much loss we have, we can compare the two expressions in the power limited regime. So if I'm going to plot the curves for the two cases, I'm going to plot the spectral efficiency on the y-axis as a function of EBNO. You can easily convert from SNR to EBNO using the relations we discussed in chapter 4. Now, we first plot the Shannon limit. The ultimate Shannon limit is minus 1.59 dB. This is going to be 0 dB here. And if I plot the Shannon limit, it will be some curve like this. It increases with EBNO, and at minus 1.59 dB, it's 0. This point here is 1. Some point here is 2. So actually, I want to draw this horizontal asymptote for rho equals at 2, when rho Shannon equals 2. So this is my rho Shannon. Now I can also plot rho binary, right? From this expression here. I can never exceed 2 bits per 2 dimensions, so I had plotted this horizontal line. So as EBNO goes to infinity, the most I can get is 2 bits per 2 dimensions. If EBNO is smaller, I can do better. I cannot do better, so I will be doing worse and worse, and I will be always below this line. And ultimately, it can be shown that I will have the same Shannon limit here. So this is rho binary. And the main observation here is, if I'm in the power limited regime, which is, say, in this part of the curve, let's say around 1 bit per 2 dimension, the gap here is quite small. In fact, this gap can be shown to be at most 0.2 dB. So if I want to achieve a certain spectral efficiency, if I impose a binary signaling constraint, the additional EBNO that I require when the spectral efficiency is 1 dB, 1 bit per 2 dimension is at most 0.2 dB. So there is not much to lose by imposing a binary signaling constraint. Said in different words, if you had the best possible binary linear code followed by a binary signaling constellation, the most you can lose is 0.2 dB. And so this type of an architecture does make sense. There are a lot of details that the next point will be to kind of formalize the notion of a binary block code, then specialize it to the case of binary linear codes, and so on. Unfortunately, the first thing to do is to start with some finite field theory, because there's a lot of finite field algebra involved in this algebraic block codes. So how many of you have seen finite field theory before? Okay, quite a bit. If you haven't seen it, don't worry about it. We'll be starting right from the basics. So, but I think I will be stopping here for today because I don't want to go into those details today. So.